All right, so we just looked at vertical translations of linear functions, and now let's move on to horizontal translations of linear functions. So just if we glance at the picture with these lines right here, a horizontal translation, we can see we've got line F, and we are shifting it to the left, however many units, and we end up with line G. So that's what a horizontal translation looks like. It just takes a line and it shifts it left, or it could shift it right. Horizontally, could go left or right. So part A asks, how does adding a constant k, so some number k, to the input of a linear function affect its graph? So consider the graphs of f of x equals 2x minus 4. So this is just our function, 2x minus 4. And g of x equals our f function. But do you see how what we're doing is we are adding a constant k to the input. Remember, your input is your domain. Those are your x's. So I'm taking the x and we're adding a 5. So we're adding in a constant k. We can go ahead and figure out what our new g of x function will be. Maybe off on the side, we can do that work. So g of x, and then we'll put a simplified equation right here on our line. So g of x is equal to our f function, but it's not f of x, it's f of x plus 5. So what we're going to do is we are going to take the x plus 5 and we are going to put that in for any x's in the f function. So g of x is equal to your f function, but it's not f of x, it's f of an x plus 5. So we just replace the x with an x plus 5. So our function would be, we have 2 instead of an x, we're going to replace that with x plus 5 and then minus 4. So what we did is we added a constant k to the input. We're adding a 5 to our x. We can simplify this by distributing our slope. 2 times x is 2x. 2 times a positive 5 is a positive 10. I'm going to go ahead and carry down the minus 4. And then we have a 2x, 10 minus 4, those are like terms, will give us a positive 6. So our g of x function is equal to 2x plus 6. If we take a look at this graph right here, here's our f function. The 2x minus 4, we can see the y-intercept is negative 4 down here. And we have a slope of 2, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. When we add in a 5 to our input, what it does is it gives us this graph right here, 2x plus 6, or here it is, g of x equals 2x plus 6. Now our y-intercept is 6, so if we go up the y-axis, here's our 6 with a slope of 2, up 2 over 1, and we can backtrack down 2 over 1, down 2 over 1, and we get this line. What we notice is that it took our f function, and when we added in a 5 to the input, it translated or shifted our graph to the left 5 units. 1, 2, 3, 4, 5. So adding a constant k to the input, meant for that to be, there we go, to the input of a function, translates the graph horizontally by k units. I think that kind of makes sense. You know, our x's are the horizontal variable on a graph. And if we're adding a constant to the x's, it's going to shift your graph horizontally. In a horizontal translation, if the constant k is positive, so that's what we just did. We put in a positive 5, the graph is going to shift to the left. If the constant k is negative, which we didn't see that example, but I'll just tell you, if the constant k is negative, the graph is going to shift to the right. All right, so this is what I call your tricky x. It seems opposite of what it should be. If we're adding in a 5, we're told right here we actually shift to the left in the negative direction. If we are adding a constant that's negative, so it might look like x minus 5, we would actually shift to the right. So just an easy little thing you can remember is that the x is tricky. So you've got your tricky x. You always shift in the opposite direction of what it looks like it should do. So just remember, if we're adding a constant to the input where your x is, that's a horizontal shift. If you remind me in class, I'll play for you guys the song about, well, it's not really about tricky x, but it's a song called Tricky. You might actually know it. All right, let's look at just a couple more examples just to clarify and make sense of what we just talked about. So let f of x equal 3x plus 7. How does the graph of g of x equals f of x plus 9.5 compare with the graph of f of x? So what we notice is that g of x is our f function, but we are adding a constant to the input. Now, anytime we add a number in with the x, that's going to be a horizontal shift, but tricky x tells us it's going to shift in the opposite direction of a positive 9.5. So we are going to shift or translate to the left 9.5 units. That's how it compares. It's just going to do a horizontal shift. And then what is the equation for g of x? We can work that out. We just take, let's see, g of x is equal to our f function, but anywhere that we see an x, we replace it with an x plus 9.5. So our f function is 3 times x, so I'm going to say 3 times x plus 9.5, and then we've got that plus 7 on the end. And then we'll just go ahead and simplify this. We can distribute that 3. That gives us 3x. 3 times 9.5 is 28.5. I'm going to carry down the plus 7. We've got some like terms, so we can get our simplified g of x function is equal to 3x plus 35.5. One thing I do want to point out, the original f function had a slope of 3 and a y-intercept of 7. Our g of x function, when we added a 9.5 to the input, it translated left 9.5 units, but if you notice, it didn't change the slope. The slope is still a 3, but it did change the y-intercept. So let's just make a note of that when we do a translation, we will still have the same slope. That doesn't change, but the y-intercept is different. That's another comparison. All right, last question. How does the graph of h of x equals f of x minus 4 compare with the graph of f of x? So we're still working with this f of x equals 3x plus 7. So what we want to notice is that we are adding in a negative constant to the input, an x minus 4. So anytime that you are adding or subtracting, subtracting a 4 is the same thing as adding a negative 4. If you're adding that to the input, then that is going to be a horizontal translation. But remember our tricky x, it's not going to go to the left 4 units. It's actually going to translate to the right 4 units. All right, then we want to find the equation for h of x. So h of x is equal to our f function, but anywhere that we see an x, we're going to replace it with an x minus 4. So h of x equals our f function. So up here, our f function is 3x plus 7. So 3 times, and instead of an x, we're going to replace it with x minus 4. And I'm just going to continue the plus 7 of the f function because we want the f function. We're just putting an x minus 4 in for the x. We'll go ahead and distribute. 3 times x is 3x. Positive 3 times a negative 4 is a negative 12. I'm going to carry down the plus 7. We've got some like terms, so our final h of x function is 3x. Negative 12 plus 7 is a negative 5. All right, one thing I want to point out, like on the last one, when you do a horizontal translation, notice that it doesn't change your slope. The slope is still the same, but our y-intercept did change. So let's just make a note that this same slope, different y-intercept applies to both of these functions because they both had a horizontal translation.